Now we have all the pieces to put together the climatological atmospheric circulation. So we have uneven solar heating, so warmer in the tropics, colder at the poles. That drives convective circulation, and we have lower pressure under the warm air and higher pressure under the cold air. Those pressure gradients drive surface flows, and then those surface flows are deflected to the right in the northern hemisphere or to the left in the southern hemisphere by the Coriolis effect. And the Coriolis effect requires that we now have 3 convective cells in the atmosphere in each hemisphere. So warm air rising the tropics, sinking around 30 degrees, north or south latitude. Then another low pressure area up at 60 degrees, north or south, where we have air rising again. And then we have a third circulation cell with cold air sinking at the pole. So if we didn't have rotation, these highs and lows, low at the tropic, high at 30 degrees north, low at 60, high at the poles, would drive pressure gradients or drive flows based on those pressure gradients as shown here. So from the high pressure at 30 degrees towards the tropics and towards 60 degrees. But we have Coriolis. So the rotation of the Earth, as I said earlier, deflects these air masses as they head down the pressure gradient to the right in the northern hemisphere or to the left in the southern hemisphere. And notice that they are in the direction of travel. So as they move from the high down towards the low, they get deflected. So summarizing that, we have the 3 convection cells and the surface winds curving to the west in the area between 30 degrees north and the tropics, curving towards the east in the area between 30 degrees and 60 degrees, and then curving again towards the west between 60 degrees and the pole. So one of the differences between oceanographers and atmospheric scientists is the way that they label direction of currents. So in the ocean, we name currents and the direction they're going towards. So we would have a westward current or an eastward current. In the atmosphere, they label the winds from the direction they're coming from. So here in the tropics, we have the northeasterly trade winds in the northern hemisphere, southeasterly trade winds in the southern hemisphere. The mid-latitudes, we have westerlies because they're coming from the west towards the east. And then in the polar regions, we have polar easterlies because they're coming from the east towards the west. So we've talked about this a bit before, but just to summarize again, we have low pressure at the equator. So we have rising air, high pressure at 30 north. So we have sinking air, rising air, and sinking at the poles. This gives us 3 convection cells in each hemisphere of the atmosphere. So we're closest to the equator, we have the Hadley cell, named after a British atmospheric scientist, and that goes to about 30 north or 30 south. In the mid-latitudes, we have the Ferrel cell, which was named after an American atmospheric scientist. And then we have the polar cell, which is the one that makes the most sense because it's named after the region of the globe it's in. And that we have Hadley, Ferrel, and polar cells in the southern hemisphere. As the air rises in the low pressure regions, it's bringing moisture from the Earth up into the atmosphere where it will eventually rain out again. So the low pressure regions are regions of precipitation. The high pressure regions are bringing dry air down from upper atmosphere, and so we have drier conditions on the land below that. So typically rainforests are found around the equator, and the great deserts of the world are found around mid-latitudes, 30 degrees or so. The jet stream, which you may have heard of, which is a very strong upper atmosphere current, of air current, are found in the areas between the different cells. So the subtropical jet stream between the Hadley cell and the Ferrol cell, and the polar jet stream between the Ferrol cell and the polar cell. So we've seen that the climatological winds are made up of several wind belts. So in the tropics, we had the trade winds, so northeasterly in the northern hemisphere, southeasterly in the southern hemisphere. And the Ferrol cell, so between about 30 degrees and 60 degrees, we have the mid-latitude westerlies, and then above 60 degrees in each hemisphere, we have the polar easterlies. In the equatorial region between the two Hadley cells, we have what's known as the doldrums. So you probably heard people say that they're in the doldrums. It's an expression, and it's because in the days of sail, you could get becalmed there for days on end. Between the Hadley and Ferrol cells, we also have an area of relatively calm winds. These are known as the horse latitudes. From what I understand, they're called the horse latitudes because it was about that time when you're sailing out of England, you're about as far away from England that you needed to be to have paid off your pre-sailing wages in the days of sail. And then between the two Hadley cells as well, we have the intertropical convergence zone, which is the atmospheric equator. So this is the atmospheric equator here. As you can see, it's not on the actual geographic equator, and it varies in latitude between summer and winter. It's generally in the northern hemisphere most of the time. Around the Indian Ocean with the monsoons, there is the largest distance between the ITCZ between summer and winter. And the ITCZ is a very wet region. In the light and nutrients video at the end of section 4.1, I showed this figure, and so now you can understand where these dust clouds are coming from or why they're in these locations. So off the Great Deserts of Africa, we're in the northeasterly trade wind belt. At the latitudes for the deserts around China, we're in the mid-latitude westerly wind belt. So we're seeing that the dust is being blown to the east at that point. So just finally, we're going to see in the next section that the climatological winds drive the climatological upper ocean circulation.